Now in this video we will discuss what is expansion work. So we will discuss expansion work. And then we will discuss how expansion works are measured. So that is measurement of expansion work. And then finally at the end we will discuss when this work is maximum. So when we have expansion work, that is maximum. So maximum work, what is the condition when we will get this work as maximum? So let us say first we introduce concept of work. So what is work? Let us say I have a stone that is kept on an earth. If I lift this a stone to a height h, so if I lift this stone to a height h, let us say now a stone is here, mass of this is m, and this stone is lifted by height of h. So if you have some idea in physics, we call there is a work has been done. So some external agent is applying a force to lift this box or lift this stone. Work done in this case is measured and this is called mgh. So it is calculated using the formula mgh. Similarly, let us say you have another situation, you have a resistor. You can have a bulb, and this resistor, if this resistor is connected through a battery, so this is a resistor and this is a battery. So what is happening? This battery sends current through this resistor, basically flows electrons. So electron flows through this circuit. This means now this time this battery is doing work. Are you getting? So this time this battery is doing work. In this case some external agent is doing work. This kind of work is generally called mechanical work. So we call this kind of work as mechanical work, and this kind of work is basically, you can call this as a electrical work, or you can also call this as a chemical work, because the energy that is coming from chemical changes, we will call this as a electrical work. Now you can have another kind of work, that is the expansion work. Let us say you have a vessel and this vessel has some gas. So some gas is there inside this vessel. We have gas. Now some bait is kept over this piston, and now there is inside this, I have a zinc. So zinc, so this is a piece of zinc, so zinc Zn. Now let us say I have a vessel and this vessel contains HCl. So this vessel contains HCl. Now initially I have this situation. So I have a configuration. In this configuration I have some volume of gas, some bait is here. Now if I pour this HCl to this vessel, so what will happen? So if I pour this HCl into the vessel, that is, if I lift down, so if this vessel is made down, that is all the HCl. Now I have zinc and I have HCl. So zinc starts reacting with HCl. Now initially volume was basically fixed, but now what will happen? Some gases will be produced. So zinc will react with HCl, zinc reacting with HCl, and it will form ZnCl2 and it will produce hydrogen gas. So a gas will be produced. Zinc is a solid, HCl is a aqueous, and ZnCl2 is also aqueous. So using this, if I have this chemical reaction, some gases are produced. So this gas, hydrogen gas, is produced in this reaction. Now what this gas will do? This gas will try to lift this piston. So after some time you will see the configuration of vessel has changed. So initially I have something like this. After some time the piston will be here. That is, this piston will be lifted by some amount. So I have reaction, some more gases are produced, and finally this piston will again reach to the equilibrium. Now why this is happening? Because you can see inside this, so there is a pressure outside. So we have external pressure due to this bait. There is external pressure over this piston. So there is external pressure. Now internal pressure is also there is internal pressure. Initially internal pressure and external pressure are in equilibrium. So if I say this is condition number 1, this is condition number 2, now this is condition number 3. So in condition number 1, what we have P external is equals to P internal. That is a situation of equilibrium. Now if I disturb this equilibrium, that is if I pour this HCl, zinc react with HCl and it forms some hydrogen gas. Now this hydrogen gas has to has into this volume. But now this volume is not fixed. Since the volume increases, pressure has to be increased. Are you getting or not? So if pressure increases, so now internal pressure is more than the external pressure. So in this case, since the volume is, so some gases are coming, so pressure inside this vessel is increasing. Now in situation number 2, what is happening? Internal pressure is basically greater than external pressure. As soon as some gases comes out, now the pressure is high because we have more number of moles here. So to reach the equilibrium, this pressure, so this piston goes up, and finally there is again an equilibrium. In this case, situation number 3, we have P internal is equals to P external. So this is again equilibrium. So if you see in this whole process, this mass, that is this bait, has been lifted some height. So from here to here it has lifted some height. So this means there is some work. This kind of work is basically called expansion work because in this case gases are expanding. In chemistry we are mainly interested in expansion work. So work due to expansion of gases, expansion is called expansion work. Are you getting? In chemistry, mainly we are interested in evolution of gases. So there are many chemical reactions that produces gases. So that's why we are mainly interested in expansion work. So chemical reaction produces gases. So in chemistry or in chemical systems, we are interested in expansion work. Now we will discuss the sign of this work. So let us say we discuss sign of work. I think all of you know what is system and what is surrounding. If you know the system and surrounding, things will be easy for me. Let us say I have a system. So this is my system. If some energy flow into the system, let us say some energy flow into the system, that is the system is gaining the energy, we call this as a positive. If some energy goes out of the system, that is some of the energy of the system has decreased, so some subtraction of energy, so we call this as a negative. So what we have? We have energy coming into the system is positive, energy going out of the system is negative. Are you getting? So this is my system. Some energy is coming in, positive. Some energy is going out, that is negative. Now, so we will basically interested in energy. So if you remember the sign of energy, then you can decide what is the sign of work and what is the sign of heat. Because work and heat both are a type of energy. So work and heat both are a form of energy. How this is so? Only difference is in case of work. In case of work, energy flows into a constrained motion. So you see, let us say you have a battery. Battery pushes this electron. So basically in this case, electron has a certain path along which this can flow. In this case also, this mass, so molecule or molecules or particles of this masses moves in a certain fixed direction. This kind of flow is called work. So if energy flows into a certain direction, into a constrained direction, this is called work. If energy flows in a disorder motion, disorder way, we call this as a work. Sorry, we call this as a heat. So I have a energy here, and now this energy is flowing in uncertain way. So motion is random. So energy is flowing randomly. We call this as a heat. So what is the molecular picture? So we have, if motion is ordered, flow of energy, so we can call flow of energy in an orderly manner. If this happens, we call this as a work. And now flow of energy in a disorder manner, or in a random way, we call this as a heat. So now I think all of you are able to understand. Basically heat and work both are form of energy. So you have energy, it can be, so if you give some heat, you basically increasing the energy. If you do some work, you are increasing the energy. Similarly, you can decrease the energy if you take some work, or you can decrease the energy if you take some heat. So in both cases, basically you are decreasing the energy. Are you getting? In both cases, you are increasing the energies of system. So now we have, things are very easy. So this is my system. If energy comes, this is positive. If work comes, this is positive. If heat comes, that is Q, for heat we write Q, this is positive. And now same is negative also. In this case, if I have my system, if energy goes, this is negative. If work goes, this is negative. And if heat goes, this is also negative. So this is a sign convention for heat, work and energy. Now let us say I have a vessel, and this vessel is basically having a piston. This piston is movable piston, it can move. So this piston is a movable piston. Inside this we have gas. Now let us say cross-sectional area of this piston is A. So what is A? A is the cross-sectional area of piston. So A is the cross-section area of the piston. Now outside pressure we have, so there is a pressure that is applied from outside. Let us call this pressure as P external. Now this gas somehow, I don't know what is the reason, maybe there are some reaction that is taking place. Due to that reason this gas has expanded, and now this piston has moved by some amount. So due to some production of gases inside, some chemical reaction is going on. So some chemical reaction is going on, some gases are produced. So due to that this piston has moved by certain amount. Let us call this amount is h, or we can call this as a x. So let us say this has moved by distance x. So what is x? X is movement of piston. Movement of piston. So by x amount this piston has moved. Now we want to find what is the work that this has basically done on the surrounding. So this part, these all gases are my surrounding. So what is happening? My system is basically pressing this side. So system is doing work. So system is doing some work on the surrounding. In this case, this is basically expansion case. System is doing some work. So we can say here, system is doing work on the surrounding. Doing work on the surrounding. So you see, we are interested in how much work it is done. It is done in this case. So let us say now I am only interested in magnitude of work. So physics we know, force into displacement, F into displacement we write S. Force into displacement is work. What is the force that is applied? So force is pressure is P external into area is force. So P external, pressure into area, that is nothing but force. What is displacement of this piston? X is the displacement of this piston. So this is your P external into A into X. This is the amount of work. So this is the magnitude of work that system has done on the surrounding. Are you getting or not? Now let us say initial volume is Vi. So my vessel initial volume is Vi and the final volume is Vf. So we can write this extra volume, that is A into X. So this extra volume is A into X. So we can write Vf final volume minus initial volume is nothing but A into X, where A is the cross-sectional area. So now the same thing can also be written as P is equals, W is equals to P external, AX is nothing but V final minus V initial. That is change in volume. So we can also write P external multiplied by delta V, or we can write dV. So this is dV. So what is dV? So I am giving a fancy word here, dV for this. So this is my dV. So Vf minus Vi, I am giving this as a dV. So this is the work. Now this is a magnitude wise correct. Now let us say check the sign. What is the sign of work in this case? Now system is doing work on the surrounding. So system is losing some energy. So system is losing some energy. This means this work is negative. Are you getting or not? What is the sign of dV? That the final volume is more than initial volume. That is, this sign is positive. So dV is positive. So now if I check the sign both sides, this side I have a negative quantity, but this side I have a positive quantity. So this can't be. So what we do is, we make the equation sign wise correct. To do that, we have to multiply a sign of negative this side. So to make the equation sign wise correct, to make the equation sign wise correct, we put a minus sign, we put a negative sign right hand side. Are you getting or not? We put a negative sign simply right hand side. So we have work done is equals to P external into dB with a negative sign. Now this work is done by the system. You see, this is the work done by the system. Are you getting? So this is the work done by the system. So work done by the system. If you wish, you can derive the same expression for compression case. In this case, what we have done, this is a case of expansion. Now you can derive the same equation for compression case. You can do yourself. We can do the same thing, same derivation for compression case. That is, let us say I have initial volume is somewhere here. So now piston is here. So this is my piston, gases are here. So we have gases here. Now this side we have external pressure P external. So this side pressure is P external. Now let us say due to the P external, now this P external is high. So this external pressure is trying to push this gases. So now this gases has been pushed. So finally I have, so due to external pressure, this means some person is pushing these gases. This gases has been compressed. Now let us say this volume is Vf. This volume is Pi. And now the movement of piston, so this distance, that is the movement of piston, is again x. If you follow the same derivation, you will find work done in this case again P external into A into x. This will come out to be P external into A into x. Everything is same. Force is P external into area, and to displacement is again x. Now I will check the sign. Only thing is sign is important in this case. What is the sign of work? Because system is gaining some energy. Somebody is doing work. Somebody is pushing on the system. This means somebody is losing its energy and giving the energy to the system. This means system is gaining energy. This means system is taking some work. So some work is done on the system. So work is positive. What is the sign of dV? Ax is nothing but dV. So let me write one more line. So W is equals to P external into dV. W is positive. What is the sign of dV? dV is nothing but final volume minus initial volume. Are you getting? That is, we are writing dV as final minus initial. So what is my convention? So when I am writing dV, this means final minus initial. But this time final volume is smaller, initial volume is larger, so this term is negative. So this term is negative. So to see this equation is not sign by is correct. So to make the equation sign by is correct, we again have to multiply by a negative sign. So we have to multiply by negative sign, and this time again work done is minus P external into dV. So now we have a expression for expansion work. So whenever we have expansion work, expression is, we can calculate using this formula P external into dV. Are you getting or not? So this is the expression can be used to calculate expansion work. Generally chemical system evolves gases, and that's why we have expansion work. Now we will discuss some consequence of this equation. Work expansion work is minus P external into dV. So I have expansion work is minus P external into dV. So let us say I have a vessel, and this vessel is closed by a piston. This piston has some bait. Now if I ask when this work is minimum, that is when this work is minimum, so I am interested in minimum work. So when this work is minimum, this is possible only if P external is 0. If I have internal pressure 0, that is the work done is 0. So when P external is 0, this means there is no weight here. There is nothing here. Simply this is expanding without any pressure. So in this case, P external is 0, work done is 0 because 0 into dV is 0. So work is 0 and this is minimum work. So what is the minimum work possible in this case? So minimum work is 0. Now in this case I can say there is no weight, so this is simply free expansion. So this is a case of free expansion. So in case of expansion of gases, minimum work is achieved when we have free expansion. So minimum work is possible in free expansion. Now next is, you can think yourself, we can talk something about maximum work. When this is possible, when I will have maximum work, that is my work is maximum P external into dV. So I need this work to be maximum when this is possible. You can say this is possible only P external is maximum. So it looks like if I have P external is maximum, but now I have a problem. P external maximum can be anything. I can have a large number of bait. That is, I can increase the pressure here by putting a large number of bait. But in that case, gases will not expand because gases can push certain weight only. If I have internal pressure that is very less than external pressure, gases will be compressed. So we cannot have expansion. So I need a expansion. So I have a limit on external pressure. I can apply only certain weight. I can apply the weight so that the pressure external is equals to internal pressure. Then only I will have expansion slightly even less. So I have slightly less external pressure than internal pressure, and then I will have expansion. In that case, I will have maximum work. Theoretically, I can say when P external is just equals to P internal, expansion work will be maximum. Are you getting? So let me try to explain this again. When P external is slightly, when P external is just equal to P internal, in this case expansion work is maximum. So this means if I want to take maximum work from this system, I have to put the bait so that P internal is just equals to P external. So my P external is just equals to P internal. Basically P internal is slightly greater than P external. Then I will have external expansion. So this is the possible case for expansion. And now this has to be achieved at all point of time. Let us say explain this thing in more detail. So I have a vessel. This contains some piston. There are some gases. I have high pressure. So now I have bait. Some baits are here. Now internal pressure, I have P internal, I have P external. So P internal is slightly less than P external. So I have P internal, in this case, sorry, P internal is slightly greater than P external, just greater than. So what will happen? This gas will expand. So this gas will expand, and now it will reach here, and it will reach here, and it will happen this internal pressure is equals to external pressure, because as gases will expand, pressure inside will decrease, and it will decrease, a time will come, P internal is equals to P external. So no expansion now will happen. So what we will do? We will remove this bit, that is I am decreasing the P external. So now I will have second situation. If I remove this bit, I will have this pressure. Now P external is slightly less than, and now P internal is again different. Let us call this as P dash internal. Now P dash internal in this case is again slightly greater than P dash external. So now expansion will again happen. So it will go to some more. So expansion will be slightly more. So I will reach somewhere here, and now again equilibrium will be achieved. That is P external, P dash external is equals to P dash internal. If I go on the process, what will happen? If I slowly remove this bait, will get the maximum work in this situation, because at every time P internal is just equals to P external. So if I want to get the maximum work from this system, what I have to do is I have to remove the weights. I have to remove the weight very slowly. I have to remove a very small bit, point 1, let us say 0.0000. So I have to remove the weight very slowly. Are you getting or not? So in this case, work done will be maximum. The same thing we can show with the help of graph. Let us see. On the x-axis, we are plotting the volume. So on the x-axis, we have volume. On the y-axis, we put the pressure. Let us say P external. Initially, my volume is, let us say I have a very, so this is a case of expansion. So let us say I have initially, this is the external pressure, and initial volume is this. So I have this point. So what I am doing here, so this is my original situation. So at this point, this is the pressure, outside pressure, external pressure is this, and this is the volume. Let us call this as a volume, initial volume I have here. Now, since the internal pressure is greater than external pressure, this system will expand, so volume will increase. So volume will increase. At a time will come when the internal pressure becomes equals to external pressure, and now system becomes in equilibrium. So this is the case when system becomes in equilibrium. So this is the first case of expansion. So you see from here to here, so these two things we are plotting on the graph. So this situation, that is the first situation, first expansion situation, that is I am having here. The gases are expanding, and a time comes when equilibrium reaches, that is the P internal is equals to P external. Now my system is in equilibrium. Then what I do? I reduce the external pressure. So my external pressure is now somewhere here. Again, gases will expand. So gases will expand, and a time comes when equilibrium reaches. So I will have something of this kind of situation. Now if I remove some, so this situation, this graph, this is this part of the graph. So second box denotes this. So I can say this is the first part and this is the second part. So this situation is the first part and this situation is the second part. Now if I continue, keep goes on, what will happen? I will have something like this. So in this case, this is the case of work. Now if I keep this weight so small, we can get a continuous graph. If this distances is nothing but the corresponding to weight loss. If these weight loss are very small, what we will get? We will get continuous graph. So we can get something like this. So if I lose weight very small, if we decrease the pressure, with an infinitesimally small amount. We will get a continuous curve. And now this curve will look something like this. So this side I have pressure, this side I have volume, and this kind of curve I will get. Are you getting or not? And the area inside this curve, that will give you the work done. Now this work is maximum. So this is the work done. Are you getting? So this is the work done, and this work done is maximum. So this is maximum work. So this kind of process in which system always remains in equilibrium with the surrounding, that is P internal is always equals to P external, are called reversible process. So now we can define something a reversible process. So what is reversible process? Now if you see in this case, what I am doing, my expansion is taking place at each time, at each point of the process, internal pressure is same as external pressure. So at each point of the process, at each point of process, internal pressure is same as external pressure. This kind of process is called reversible process. We have another definition for reversible process. If you see, if you decrease a bit, system will move in this direction, and if you increase a bit, system will move in this direction. So I can say a slight increase in the stress or slight increase in the pressure, because in this case stress is pressure, changes the direction of equilibrium, changes the direction of process. In this case, if I increase the bit, the motion will have in this way. If I decrease the bit, motion will take place in this way. A slight decrease in or slight change in pressure. So reversible process can also be defined as a slight change in pressure or change in stress changes the direction of process. This kind of process is called reversible process. So now I can say maximum work is achieved when the process is reversible. So fancy word we have here. So the same thing, we can call this as a maximum pressure, maximum work is achieved. So maximum work is achieved in a reversible process. Now we will calculate an expression when I have reversible isothermal expansion work. So we will basically derive an expression for reversible isothermal expansion work. What is the meaning of isothermal? That is, the temperature is constant. So I have a process in which temperature is constant. That we can do. Let us say I have a water bath. So I have a water bath here, and let us say my system inside this water bath. So this all expansion is happening inside this water bath. So this is my system. Now this expansion is happening inside this water bath. So some pressure is there, external pressure is there. So this water bath has a constant temperature. So I can say the whole process is happening under a constant temperature. This kind of process is called isothermal process. So this is a constant temperature. So now I can say my process is happening at a isothermal process, constant temperature process, and this process is reversible, that is P internal is always equals to P external. Theoretically it is impossible. We cannot have a P internal is always equals to P external practically, but theoretically we can derive an expression when P external is just equals to P external. So we can find work done. Work done expression I have minus P external into dV. Now my system, let us say, expand. In this case, since the system is reversible, I can write P external is equals to P internal. So P internal, so now I can write this is minus P internal into dV. I can also assume the gases is ideal. So now I can write PV is equals to nRT. So what we have P is equals to nRT divided by V. So we can have nRT divided by V dV. Now I can take nRT dV by V. This is minus, so this is my work done. I can integrate this one, so to get the total work. So let us say I have a small work, I can integrate to get the all work. So work done, that is basically sum all the work. Integration is nothing but summation, and initial volume is Vi and the final volume is Vf. So we will have minus nRT, and if you know integration, this is nothing but ln V. Limit goes from Vi to Vf. So we will have here W is equals to minus nRT ln Vf minus ln Vi. So if I take use of logarithmic formula, that is ln final Vf by Vi. So maximum work, so basically in this case work done will be minus nRT ln Vf by Vi. So this is the maximum work in case of isothermal process. Since this process is reversible, so this is the maximum work. So we can say this is a isothermal reversible work. Now see, if my Vf by Vi is greater than 1, that is the final volume is greater than initial volume, my work done is negative. So I can say logarithmic is negative because now positive, because a number greater than 1 log will be positive, minus 1, so finally work will be negative. And one can expect this because system is expanding. If I have this is less than 1, that is Vf by Vi, this is less than 1, work done will be positive because this number is less than 1, a number less than 1 logarithmic negative, and negative positive. And this is also possible because my system is in compression, because V final is smaller than V initial. This means system is in compression. So this is a case of expansion, and this is a case of compression. Another important result we have, if you do the same change in volume, that is Vi to Vf, at different temperature, work will be more. Are you getting it out? So if you increase the temperature, work done also will increase. So this means if you are changing from V1 to V2, and the work done in one case, let us say this goes process is something like this. So this is the work done at lower temperature. If you change the temperature, work done from V1 to V2, I am going again from V1 to V2, but work done will be higher. So T2 is greater than T1, W2 will be basically greater than W1. So if you change the temperature, work will be different. If you see, in this whole video we have discussed some important concept. First concept, we discussed what is work. We discussed something about expansion of work. We also discussed heat, work and energy all are a form of same thing, that is the work and heat is a form of energy. And then we discussed something about expression for expansion work or compression work, that is minus P external dV. And then we discuss reversible work, when you will have maximum when the process is reversible, work is minimum when the process is in free expansion. And finally we derived one expression for reversible expansion work in case of isothermal, and expression is minus nRT ln Vf by Vi.